Welcome back to the second part of the AM session. So may we now invite our next speaker, Mr. Patrick Chiang, E4 PhD student in physics. Mr. Chiang, please.
Okay. Thank you. So I'm Patrick Chiang. So today I will present a topic about how to simulate the physics at extreme on behalf of our group mate and also my supervisor, Professor Johnny Lee. So let's get started. So this is the outline of my talk. So first, I will give some very brief introduction about the physics behind and the motivation why drive us to develop our simulation code. And then secondly, I will show some our original result, and then comes to summary and question sections. So one of the interesting questions in physics is what is neutron star? So the figure here shows our current understanding of a cool neutron star. So it constructs with a different layer where the rho knot here represents a nuclear density, which is roughly 10 to 14th gram per cm cubic, so which is extremely dense material here. So to be honest, the physics at that extreme condition is a little bit beyond our understanding of physics. So in short, we actually don't know what neutron stars made of. So to understand the physics behind, to understand the equation of state at such extreme condition, we may investigate in following two ways. First, to study how the neutron star is made. So neutron star is actually often made by core collapse supernova. So here's at least some technical details about this core collapse supernova, but to make it more simple, basically all you need to know is that supernova in terms of physics basically have two types. One is once it explodes, nothing left, and one is that some remnant is remained. So of course, neutron star is one of the possible remnant of core collapse supernova. So here's a rough cartoon about how the core collapse supernova works. So the death of a massive star, which is usually 10 or to 100 solar mass, and then it starts to collapse and compress all the matter together at the center. So it formed a proto-neutron star, as shown in this slide. So it depends on different factors. The dynamics here is actually extremely complicated, and currently at the current stage of the research, people actually don't really know exactly how to drive the explosion. So there are a lot of mechanisms, but anyway, so if the shock is revived, then the thing will push out again, and then result a supernova explosion. Otherwise, all the matter will collapse back to the center and form a black hole. So this is an example of the supernova SN 1978A. So the left panel shows some electromagnetic observation or detection of that event. The right-hand side shows not only the optical band can be detected for such event, it also radiates neutrino. So the right-hand side here shows that the neutrino signal at different detectors. And also, at that time, the gravitational wave detector is not yet ready, but core-collapse supernova is also one of the predicted source of gravitational waves. So actually, gravitational wave is expected. So here's an example of a simulation of a core-collapse supernova. So this is the extracted gravitational wave. As you can see, it's extremely complicated. And indeed, many details of physics is left behind this short amount of signals. So another way to investigate the structure of neutron star is through binary neutron stars. So here's again a cartoon shows how the binary neutron star works. So initially, two neutron stars in spiral to each other, and then they're getting closer and closer, and eventually they merge together. And then after some equilibrium phase, they will form a so-called post-merger state, and then eventually form a remnant here. It could be a black hole or a hypermassive neutron star. So this is the same cartoon with slightly more technical details, is that actually to investigate the dynamics such as binary neutron star, we need to take account of many microphysics, such as how the neutrino interact with others, and the nuclear physics and hot equation of state and so on, which is one of the holy grail of this kind of study. So again, if you extract the gravitational wave signal from the binary neutron star, here's an example of some particular simulations. So as you can see, there's a few, you can separate the signal in a few parts. Firstly, we have an in spiral part. So this part can be approximated by some analytic techniques. So you may say, right, at this stage, we don't really need simulations. And however, in this merger phase, this is highly nonlinear, and it is impossible to express the waveform during this stage accurately with some analytic expression. So it is better to have numerical simulations from this stage. And then also the post-merger stage is a quasi-equilibrium state of HMNS stand for hypermassive neutron star. So again, it could be many nonlinear effect comes out during this stage. And then finally, it might form a black hole, so it goes a rain down, and the signal shuts off. So, so actually, we really need numerical simulations to investigate such complicated system. However, if you write down all the required physics for such systems, you may need the 4 ingredients shown in this slide. So we need to describe the hydrodynamics, the general relativity, and some microphysics, and also the neutrino transport. So, and also the such problem, of course, a multi-dimensional problem, a lot of rotation, fluid instability might come out, and so on. So, so technically, if we want to numerically solve this kind of system, we need to at least solve the following equations. But I'm not going to go deep the detail here. But the key message is that they are highly nonlinear and no way to express them analytically. So many years ago, people are investigating, would it be possible to numerically simulate the dynamical space-time? And it turns out extremely difficult. So this is one of the snapshots at that conference. So let me skip it now. So in order to tackle the problem such as I described just now, we developed our own numerical code called GMU. So here I list some technical details, but let me simplify it a bit. So this code can be used to dynamically simulate general relativistics, magnetohydrodynamics problem, and can be run parallelly with a lot of CPUs and able to resolve different length and time scale, and can be used to can be set up in different geometries, or different symmetries can be imposed. So here I show you some example. However, I will not go through the details. So this is some code test of our code. So this is a relativistic jet, and this is a rapidly rotating neutron star. So as it really close to the Kepler limit, so some of the matter flow out during the dynamical process. So also we have tested this code with migration of neutron star. That means initially compact but not stable neutron star will expand a bit and fall back to with the same mass but more stable neutron star here. So not only we have gone through this code test, actually GMU has already applied in a physical problem. For example, here we investigate how and the origin of the frequency of the gravitational waves from binary neutron stars. So this is our summary. So actually we need numerical simulations to study the physics of compact objects. And the code we develop is primary, but not exclusively to study the compact objects. But since it is actually a generic magnetohydrodynamic code, so it can be used, for example, the next speaker might talk something about it, the star formation and so on. And also the high performance computing is the key to resolve these puzzles. So more to come, and hopefully we got some chance to collaborate together. So this is pretty much from my talk. Thank you.
Thank you, Mr. Chia. So questions are welcome.
Oh.
We have a question from Professor Song. So
Okay. I have a question, maybe it's more of a clarification. When you mentioned the binary neutron star, are these stars really made mostly neutrons? The binary neutron star you mentioned.
Okay. So this is actually go back to the very beginning of my slides, is that what actually neutron star makes of. So actually we don't know. Actually we don't know whether it is made of neutrons only and so on. There's a lot of different models to describe the physics inside the neutron star, but I would say definitely not neutrons only, but with something we don't know yet.
I was just wondering if suppose it's a neutron star, with magnetohydrodynamics, that typically is applied to the plasma-like species, and that actually has the magnetic motion connected with the charged species. If it's a neutron, then would the magnetohydrodynamic code still be applicable to the neutron star or not?
Okay, this is a very good question. So so let me put it this way. So what you are asking is about the time scale of different physics. As we know, hydrodynamics is described some more macroscopic behavior of the system. So you might worry about is it accurate enough to resolve the dynamics of, for example, the electron or neutrons and so on. So so that we need to firstly model such system Fermi-logically. That means with some approximation or with some understanding of the system, we simplified the physics a bit and write them down or derive a so-called equation of state. That means we relate the pressure and the density and the temperature and so on. So this is pretty much like the relation between statistical mechanics and thermophysics. So once we obtain the equation of state, then we can, of course, perform the simulation. But the question is, which equation of state is correct? It is not yet known. So the first step is to obtain the equation, the correct equation of state. And then the next step is investigate more in detail and study how to resolve the same equation of state from the currently unknown physics.
Yeah, I would agree with you on the checking the equation of state, whether that's really applicable or not. Because if you have a binary neutron star, and you also have a proton neutron star.
Yeah.
And that, if the equation states are applicable to one, it might not be applicable to the other. But if we're just force-feeding the equation of state into the state, then there is a sort of, you use all parameters to try to make it a force feed.
Yes, so that's why numerical relativity is so challenging that you actually bring out the point is that the equation of state described cool neutron star is actually not exactly the same as the one we use to describe hot neutron star or proton neutron star. So many thermal effects need to be taken into account as well.
Okay, thank you.
Thank you, Professor Song. We have one question in the chat room. You may refer to the chat room and respond to the question.
Okay, so let me rephrase the question a bit. As Steve is asking, is my simulation method based on finite element? Are there long-range interaction that makes paralyzing? Oh, okay. So the first one is the code is based on finite volume. However, the way we solve the Einstein field equation, finite difference is adopted. So the long-range interaction is actually yes. If you let's forget about the Einstein field equation. Let's consider it's just a Newtonian gravity problem. So for a Newtonian gravity, we need to solve the Poisson equation, so which is a elliptic type equation. So we need to simultaneously solve at the whole computational domain. So this is the most challenging part for when we try to parallelize our code. For hydrodynamics, everything can be done separately. So at the moment, actually, we have another group member try to implement so-called some neutrino physics into the code, and he is actually facing the problem you raised, is that because there are long-range interactions, so that the parallelization is not that straightforward.
Thank you very much. Thank you, Mr. Chang. May we now invite our another speaker, Qilao, from the Zoom to present.
Okay. Hello, everyone. My name is Qilao Gu, supervised by Professor Huabai Li of Star Formation Group in the Department of Physics. And it's my great pleasure to have an opportunity to share our research result here. The topic of my talk is Cosmos campuses, how to reason and what have we learned. As we all know, we are made of different atoms, hydrogen, carbon, oxygen, and so on. And nearly all these atoms, except hydrogen and helium, are actually created by the stars. Atoms in our bodies may come from stars light years away and have traveled a billion years in the space. We are from stars, but how do stars form? How do stars form? There are lots of molecular clouds in the interstellar space. Molecular clouds are full of molecular hydrogen and dust. Dense parts of molecular clouds would collapse due to gravity, and the cloud would fragment into several cores, and these cores would keep collapsing into protostars, and then T-Tauri stars, and then pre-mean sequence stars. And finally, young stellar systems are born. So in short, stars are formed from gravitational collapse of the dense part of molecular clouds. But the story is not that simple. This is a cover story of nature astronomy. These dark regions these dark gases are actually molecular clouds, and they are full of molecular hydrogen and dust. Look at these two clouds. Pipe is so dim and starless, while Ophiuchus is such starry and full of stars. Why these two adjacent clouds are so different? Let's try to uncover the answer in today's talk. Okay, so now let me introduce the three major players in star formation process: gravity, turbulence, and magnetic fields. Of course, gravity make dust and gas collapse, and it also compress magnetic fields and drives the turbulence. And turbulence, it will against gravitational contraction and compress magnetic fields as well. And the last one, magnetic fields will channel the gravitational contraction and the anisotropy turbulence. The interacting between gravitational magnetic fields and the turbulence are very complex, which makes the star formation process very hard to be fully understood. Today, let's talk about one of the major players, magnetic fields. So how to trace magnetic fields? As we know, magnetic fields are invisible. And on the Earth, we can use the compasses to trace magnetic fields. When the compasses show the direction, we can know there is magnetic field. So in astronomy, we also have such cosmos compasses to trace the magnetic field in space. That is dust grains. So how can dust grains be the cosmos compasses? Interstellar space is full of hydrogen, but it is so difficult for hydrogen atoms to collide to form molecular hydrogen in such empty and cold universe. So how do such many molecular hydrogen form? Let's try to answer the two questions together. First, hydrogen atoms are absorbed onto the surface of dust grains, and then the formation takes place after hydrogen atoms migrate along the surface to particular catalytic sites. By the energy released from the formation of hydrogen-hydrogen bond, the molecular hydrogen will then be ejected from the dust grain and acts as a mini rocket, spinning up the dust grain. Since the formation takes place only at particular positions on the green surface, there will be a seismic torque, and the spin axis will finally align with the short axis after energy dissipation. For the same reason, we align car wheels to avoid the energy waste. And the spin will generate a magnetic momentum parallel with the rotating axis due to Burnett effect. And just like a laboratory top, the grain will float in the sea of magnetic field with the spin axis aligned with the magnetic field. So the final result would be that dust grains are perpendicular to the magnetic field. Based on the formal fact that the short axis of dust grains are aligned with magnetic fields, which means the long axis are perpendicular to the magnetic field's orientation. We now have two methods to trace the direction of magnetic fields. The first one is called starlight polarization. As we know, the light from a star is unpolarized. But when the star of a background star passes these aligned dust grains, the starlight would be slightly more blocked along the long axis of the dust grains. So the starlight would be a few % polarized in the direction of the short axis. Thus, we can trace the direction of magnetic field by detecting the polarization of a background star. The other method is called the observation of dust thermal emission. These dust grains will also emit radiation, and its radiation and the wavelength of its radiation is at submillimeter level, which lines up with the grain's long axis. So we can derive the direction of magnetic field by detecting the thermal emission of dust grains as well, which is perpendicular to the magnetic field. After introducing the method to detect the direction of magnetic field orientation, now let me introduce a tool to achieve such observations. This tool is called polarimeter. A polarimeter is an instrumentation that equips on telescopes, which can help astronomers to take polarization observations. Our group, Star Formation Group, has designed a polarimeter named APOL recently. And Apple would be able to equip it on JCMT, the largest telescope in the world designed for submillimeter observation. Now let me introduce the working principle of Apple. The main components of Apple are halfway plate, this part, and the white grates here, and the turtle to rotate halfway plate. Halfway plate is used to change the direction of polarization, and white grate is a polarizer that only lets the polarization perpendicular to the wire's path. So the combination of rotating halfway plate and the white grates could make polarization signal periodically change, and we can derive the polarization angle by dealing with such periodical change signal. This is Apple in star formation group labs. This is a white grates, and this is halfway plate and a torque motor that rotate halfway plate. And here is a signal generator. We try to simulate some astronomy signal, and this is a camera which can take the signal of in terahertz frequency. And based on such choice, what we have found by detecting the polarization, we derive the directions of magnetic fields from above periodical changing polarization signal. And for every molecular cloud, we calculate the average direction of magnetic field. And thus we can get the angle between cloud elongation direction and magnetic field. And here is the result. We put the angle between cloud and field in x-axis, and then we put star formation rate in y-axis. And we have such relation between star formation rate and cloud field angle. And showing this figure, we can see the star formation rate gets smaller with the increasing of this angle, which means when a cloud is parallel with the magnetic field, it tends to bear more stars, or say a cloud that is perpendicular to molecular cloud produce less stars. This result agrees with the formal cases we mentioned. Look at the pipe and OPHIX. The red bars are the direction of magnetic fields of pipe nebula, and the yellow one are the magnetic fields of OPHIX. We can see for pipe, the magnetic fields are actually perpendicular to the cloud, and for OPHIX, the magnetic fields are aligned with the cloud. And this might be the main reason why such clouds are so different in star formation. Now, let's try to explain the result. The condition that the stars can form is the mass to magnetic flux ratio has to be above a critical value for gas to collapse against magnetic pressure. Assume a uniform linear density lambda. For the parallel case, the red one, we have the mass to flux ratio as this form, and for the perpendicular case, we have the mass flux ratio in this form. Since L is larger than D, so for the parallel case, which means the small cloud field angle 1 can exceed the critical value much easier than the perpendicular one. Thus, it is easier for the parallel case to grow massive fragment to form stars. So let's back to the formal figure. Pipe is a case of the green model, and OPHIX is a case of the red model. And that explains why OPHIX is so starry and pipe is so dim, as they are adjacent clouds in the sky. And here is the summary of my talk. The star formation process is still not clearly understood. Gravity, turbulence, and magnetic fields are the three major players. And based on the fact that dust grains are perpendicular to the magnetic field, there are two methods to trace the orientation of magnetic field: starlight polarization and dust thermal emission.
Excuse
The
me.
tool to achieve polarization observation is polarimetry, and APOL is designed by Star Formation Group of CUHK. Based on polarization data, we found that the star formation rate is lower for large cloud field angle clouds, and the reason might be large angle cases are hard to exceed critical max to flux ratio value to form stars. Okay, finally, let me thank to my supervisor, Professor Huabai Li, and all other members in our star formation group. And the questions and the suggestions are very welcome. Thank you.
Thank you, Mr. Gu. We have question in the chat room, but
Okay.
let's pop it to the chat room first.
Shall I stop sharing?
You can keep the sharing and then you may click the chat room.
Oh, I see. Okay.
I just paste a question there.
Okay. Is it necessary or how to distinguish the molecular cloud radiation from cosmos micro background in the measurement? Oh, this is a very good question. Actually, for the method of dust thermal emission, oh, let's back to the slide. This slide. For this method, actually, we cannot distinguish the radiation from CMB and molecular cloud, since this method just averages the entire line of sight emission in submillimeter level. But it is not that necessary, since the dust emission from this interstellar space is much larger than the emission of CMB. Yeah.
I think there is a follow-up question in the chat room, but I'm not sure why you choose.
Mm.
Yeah, you may follow up that question.
Oh, why we choose terahertz as interesting frequency? Since actually for the dust grains, the environment for the dust grains in interstellar space, the typical temperature is about 10 K, and thus for the Planck function, the peak frequency is about terahertz. So that's why we are interested in terahertz to observe the dust thermal emission.
Any further question from live? Oh, we have a follow-up question in the chat room.
Mm-hmm. From other frequency, oh, I think for every observation in, sub-terahertz. In my knowledge, when we take the submillimeter observation, there's a filter, a filter in front of the camera. So the bandwidth is not that large. So this helps us to get rid of the influence, help us try to get rid of the influence of other frequency. I think that the transmitted light through the dust may be partially polarized, and will it or how it will influence it. Yeah, of course. Every method for no matter the starlight method or the dust thermal emission, the light is always partially polarized, actually, not 100%. Actually, the percentage of polarization is normally 1 to 2% is such in such level. Yeah, the polarization fraction actually is very low. So that's why take a submillimeter observation is so hard, since we need to integration a lot of times observation to get a very well signal for the polarization analysis.
All right, thank you. Do we have any question from the audience here? All right, Professor Song, please.
I have a question which is more of a clarification. What are the nature of the dust that you use? What is the dust?
Uh,
Do you mean the
What-
stars that
oh.
start at the dust, or the fragment from Big Bang? That's what you call the star.
This is a very good question, and I try to answer what is dust. Actually, these dust are mainly the components of dust are mainly silicon, and some are carbon. And this dust, one source of the dust actually are the death of stars, the death of different generation of stars, and the explosion of the when a star is dead, and it will create a lot of new elements, and the body of the stars will be just fragmentation, and it will just be put into the interstellar space, and it will be the dust grains in the interstellar space.
The implication that you have is that the dust is a flake-like or plate-like. Therefore, it can be perpendicular to the magnetic wave. But in reality, I wonder whether how many of the dust grains are plate-like or flake-like. They may be more spherical-like. If so, there's no such a thing called a perpendicular or otherwise.
Yeah. That is also a very good question. The dust grains actually are in different shapes. Some researchers have researched this topic. They have developed different model of the dust grains in irregular shapes and in just very regular shapes, as I showed in this figure. And their result is actually quite similar as what I mentioned today. Since for every different regular shape dust grains, they also have a short axis and a long axis. Even for the, of course, there may be some dust grains are in spherical shape, but the percentage of such very perfect spherical dust grains are very small. So as I showed in this figure, not all the dust grains are actually perpendicular to the magnetic field. Of course, there are some typical molecular cloud, some typical dust grains not aligned with the B field very well. But the most likely orientation is aligned with the B field. Yeah.
Okay. Thank you.